frustration.
Thanks very much for the introduction. First of all, let me thank the organizer for inviting me to this very nice program. So I provide this vague title. Really, I don't know what title should be best. So maybe more popular should be multipolar frustration on top of geometrical frustration. So this is from reality to fantasy rather than from fantasy to reality. So then first of all, let me advertise this conference next year. It will be the 10th International Conference on High Frustrated Magnetism. It will be held in Shanghai in May 2020. So if you are interested, please pay attention to this conference. So the abstract submission will open in about 2 weeks from now. So this is the outline. In the first part, the first part has been already presented in KITP about 3 weeks ago. If you are interested, you can look up. So this is identifying hidden multipolar orders in some triangular lattice magnets, and we provide some new insight, and the insight can be generalized to identify other hidden order in other systems. So the second part is about symmetry-enriched UN topological order and some related field-driven Anderson-Higgs transition. So hidden order is an older subject in condensed matter physics. It has been there for about 30 years. So this is the famous compound called uranium, ruthenium, silicon, where the idea of hidden order was proposed. So in this material, in this compound, which has both conducting electron and local moment, and as you cool the system, with pressure, around 17 Kelvin, there is a phase transition. This is signaled by a peak in the heat capacity. And across this phase transition, there is a huge entropy drop. And the entropy drop is order of that, per sublattice. So this is a huge entropy drop. And below this 70 Kelvin, there is a phase which people call it the hidden order phase. Because the reason it is called a hidden order because this order parameter associated with this transition is completely invisible. So people know there must be a phase transition because there is huge entropy drop. The system becomes more and more ordered, but we don't know the nature of the hidden order, the nature of this order parameter. At very low temperatures, there is some human activity going on. So this order parameter associated with this transition and this hidden order phase is unknown after 3 decades. So many experimental probes has been suggested. This material has many degrees of freedom. So you can apply many different kinds of experimental technique to give some experimental result. So this is the summary before 2014. And these are various theoretical proposals. Most of these proposals is suggesting the underlying hidden order is some kind of multipolar order, either electronic version or magnetic version or hybrid version. So it's unclear what kind of hidden order it is right now. So the question, how do we identify the nature of hidden order, generically? So there is a very simple suggestion. So the proposal is you can try to, this is called a orthogonal operator approach. So the idea is you can find a physical observable that can be easily observed. Instead of this hidden order, this hidden order does not couple explicitly to your experimental probe, but you can find a observable that can be observed experimentally with current experimental means. So you find this operator. That operator does not, do not commute with this proposed hidden order parameter. So you can measure the correlation function of this, you proposed, physical operator, and then this dynamic correlation function or this spectra, you measure, from this correlation function of these physical observables that will reveal the structure and underlying nature of the hidden order. So this, this kind of thought has been, illustrated for hidden occupolar and quadrupolar order in triangular magnets in 2 papers of us. So we are going to apply this idea to a mysterious compound, which is this compound. It's tellurium manganese gallium arsenide. It's a triangular lattice magnet. This work is mostly in collaboration with my postdoc, Chang'e Liu. So his name means long happiness. Okay, just Chang'e, remember this name. So there are other 2 experimentalists doing neutron scattering in this collaboration. So we applied this idea to to understand the mysterious property of this material. So this is the simple thermodynamic measurement. So you apply field along, it's a triangle lattice system. You apply field in the plane and outer plane, normal to the triangular plane or in the triangular plane. So if you apply field in the triangular plane, so the magnetic susceptibility has no signal. Now the magnetization is almost zero. So if you apply field normal to the plane, so then is the response. There is a magnetic susceptibility and there is magnetization. Now when the field is large enough, the system becomes polarized. All the spin will point into the field direction. This is the heat capacity. Around 1 Kelvin, there is a peak which signals a phase transition. And if you integrate out the heat capacity, you see the entropy is log 2 entropy. So it's indicating the system is some kind of spin 1/2 degrees of freedom. But this magnetization measurement suggests the transport component, the component in the triangular plane, is completely hidden. So these variables are hidden. Only the z direction or the direction normal to the triangular plane are visible in this system. So thus it is thought, by other peoples, this material may be just a simple triangular Ising model, with Ising spin degrees of freedom. So that seems to be like that from simple thermodynamic measurement, but it's probably not the case. So this is the neutron diffraction measurement. There is a Bloch peak at K point in the momentum space, in the reciprocal space. And as a function temperature around 1 Kelvin, the peak appears. And if you do neutron scattering, if you scan for the momentum, along normal to the plane, so you see this flat line. So that means the system is truly two-dimensional. So there is no dispersion in the z direction. So it's a two-dimensional material with a magnetic order, which orders at the wave vector at the K point. So the system orders antiferromagnetically.
At which temperature?
1 Kelvin. Is this 1 Kelvin? So this system, if you do it inelastic, you see these very nice, well-defined, dispersions from experiment. So the system, and similarly, this is a theory. I will explain later how to obtain this theory. This is the energy. So this is the energy, and this is momentum. This is the omega k relation. So if you do a contour plot, if you plot at constant constant energy cut, and gradually increase the energy, you will see a nice contour in the reciprocal space, which is as follows. This is very low energy. You see this contour is the bottom of the band. And then gradually increase the energy. The contour expands. Yeah. And this is theory. So that means the system has a well-defined spin wave-like excitation with respect to the ground state. So neutron spin coupled to the local moment in the same way as the magnetic field coupled to the local moment. So neutron spin measure the d component of spin correlation function. So if the system is really Ising, you should not see any kind of dispersion. So it will be completely flat band. Now if the system is some kind of Heisenberg-like ordering without in-plane order, Heisenberg-like spin interaction without the in-plane order, the system should be this spectrum should really be a two-magnon continuum. So the presence of well-defined spin wave-like dispersion indicates the transverse component, which is hidden in your thermodynamic measurement, must be non-zero. So that presence of well-defined spin wave-like dispersion indicates the presence of hidden order. So that means the presence of this excitation indicates there is a background hidden component existing in the system. So in this material, let me explain the microscopics and then build up these models and try to understand the underlying physics. So in this system, this 3+ ion, tellurium 3+, they have this 12 F electrons, So if you do simple Hans rules, the total angular momentum L equal to 5, the spin equal to 1. If you spin-orbit couple entangle them, form this so-called J equal to 6 local moment. But on the crystal field, this floating field for the degeneracy will be broken down, and you obtain these multiple doublets or singlets. It turns out that the ground state, the crystal field ground state is a singlet. And the second excited state of the crystal field environment is also a singlet. This is really because it's J equal to 6. 6 is an integer multiple of 3.
In theory, it's measured by newtons. Crystal field level splitting, is it measured by newtons or not?
Let me continue with that.
Okay.
So these lowest two doublets, lowest two singlets are very close in energy, but then there's always a crystal field splitting between them. And these other excited states are high up in energy, it's a couple hundred Kelvin. So if one is interested in low temperature magnetic property, all these two guys are relevant for the understanding of low temperature magnetic property. And likewise, similarly, are the result the wave function. If you look at the wave function of these two singlets, they are very, very close. The combination of so-called J equals 6 and minus 6, and also some component of plus or minus 3 doesn't really matter. So these are, because these are two states, you can build up effective spin, pseudo spin degrees of freedom, using these two states. So that's the degrees of freedom. Condensed matter is a physics about the degrees of freedoms. This is the building block to understanding the fundamental property of the system. So then you can write down a model. So from this thermodynamic measurement, so the magnetization, if you apply field very strong, you get this polarized state. And this is magnetization is almost equal to 6 Bohr megaton. So this is almost the system is almost have this Jz equal to 6. So that means the system is very close to be Ising, but it's not really Ising. So the interaction between these just a second, it's very slow. So the exchange interaction between these local monon is mostly just Ising interaction, and dominated by Nielsen neighbors. And because these two singlets, they're not degenerate, locally they're not degenerate. So we introduce a transverse field, to split the degeneracy of this, these twofold degrees of freedom defined on the manifold of these two singlets. So this field, we introduce is basically try to categorize this crystal field splitting between these two singlets. So then this model become a simple, transverse field Ising model. So this is the intrinsic transverse field Ising model rather than extrinsic. So the intrinsic means this transverse field are induced intrinsically rather than extrinsically. So this J2, which one can fit, is actually quite small. So the model is basically just approximate to a nearest neighbor transverse field Ising model. So this model on a triangle lattice is highly frustrated, but it can be mapped into a dual honeycomb lattice quantum diamond model. The dual honeycomb diamond model is like a compact U1 lattice gauge theory on a 2 dimension. So it has to be confined in. Then you have diamond placated order. If you go back into spin language, you have this magnetic order. So in terms of the original spin language. So the system has some kind of order. It's some kind of 3 sublattice magnetic order. So this is the magnetic order structure out of this transverse field Ising model. So this order is outcome of this frustration and also this transverse effect, this quantum effect of the transverse field. So it's a quantum mechanical effect. So the system does not order if there is no transverse field. It orders because of the presence of the transverse field. So it's a quantum mechanical effect. After knowing the model, and one can actually obtain all these excitation spectrums. So this is the comparison between theory and experiment. So so in this system, the orthogonal operator is the z component of spin. So the in-plane component A, B direction are invisible. We only measure, so neutrons only measure the z component of spin. So the the magnetic order at K point is an indication the system orders at with SD component ordered, and it's a three sublattice magnetic structure, which is consistent with the theoretical result. And the dynamic spin structure measurement is only measuring the SD component of spin. So because only SD component of spin is visible by the neutron scattering. So if you just simply compute the SD component of the spin correlation function, you will find the reasonable agreement with the experiment. So in this context, the hidden order, hidden component is this AB plane, spin component, and the orthogonal operator is SZ. If AB plane, component does not develop any kind of order, you don't see any kind of spin wave-like dispersion, because the AB plane then is a non-zero, non-zero expansion value of the component. Then the presence of if you apply the SD operator, it will create a coherent spin excitation, by flipping the AB plane magnetic order. So then you'll create this coherent excitation. So this is the application of this orthogonal operator approach to understand the property of this system. So let me just quickly summarize this first part. So this is the presence of this coherent spin excitation and the underlying magnetic structure is the interplay between geometrical fluctuation and the multipolar local moment. So the AB plane spin component is invisible because it's a high order multipolar degrees of freedom. So it does not directly couple to the magnetic field. So the identification of this hidden multipolar order is a bit non-trivial. It requires both static and dynamic measurement. So the orthogonal operator approach can be used to reveal the dynamics of hidden orders. And this is actually quite general. You can apply this idea to other hidden orders. You can go back to think about the 30 years problem of uranium resilient silicon and try to understand the property of this hidden order in this material. Let me switch gear to something else, which is about the symmetry enriched U1 spin liquid. So this work is motivated by this very nice experimental work in cerium particle material. So this material, if you do all kinds of thermodynamic measurement and mu SR, then the system doesn't develop any order down to 20 millikelvin. So what's the ground state of this? It was proposed to be a candidate spin liquid material. So in this work, there's a paragraph. So it says, in this material, the cerium 3+ form a particle lattice, and the cerium 3+ is a magnetic ion. So it says the wave functions of the ground state Kramers doublet. So cerium has a 1,4f electron. So that corresponds to a linear combination of mj equal to ±3½ So mj is the jz quantum number. So ±3½ state. So what does that mean? So schematically, this is 4f electrons, and on the spin-orbit coupling from this, and it was j equal to 5½ and the crystal fields was split into 3 Kramers doublet, and the ground state doublet is this one, and it's a Kramers doublet because it's a odd number electron per side. Then it's a crystal field gap, which is very high, a couple hundred Kelvin. So the low energy property will be governed by this doublet, and the wave function of that is so-called mz equal to ±3½ So this is a very special type of doublet, which we call a dipole-octuple doublet. The reason why it is special is this is the wave function of the doublet. So the reason it's special is each doublet, each state in the doublet is a one-dimensional irreducible representation of the D3D point group. The reason why they degenerate is because of time-Bose symmetry. So if you apply 3/4 rotation symmetry on this doublet, Now this is threefold rotation. So you have 3/2. Mj equals 3/2. So then this will become e to I pi. This is equal to -1. So these two states, they are invariant under any symmetry operations of the point group. So it's truly a one-dimensional representation of the point group. So you can build up effective spin degree of freedom within this two doublet. So knowing how these states are transformed, and then we know how the effective spin are transformed under the point group symmetries, you can establish the generic spin model that describes the interaction between the local moments. This model is called the XYZ model. So this model is remarkably simple. It's uniform on every bond of the three-dimensional lattice. Although the local moment is an entangled object on the spin orbitals, and the orbital has orientation. When this effective moment building from this entangled local spin and effective spin and orbitals, so it should be very anisotropic both in the spin space and in the real space, in the position space. But here it's not. So it's uniform on every bond. On every bond, it has no bond dependence, but it's only anisotropic in the effective spin space. So because of this uniformity in the position space, you can do a rotation in the effective y. In the y component around the y-axis in the effective spin space to eliminate this Gaussian term. The model becomes remarkably simple. It's an XYZ model. So this model is isotropic, in the position space, but it's anisotropic in the spin space. So the reason there is no interaction, no intercosine interaction between x, z, and y is because sy transform very differently from sx and z component. That's the reason is sy is actually a magnetic octopole moment rather than magnetic dipole moment. So because this xz model, it has three parameters. And there is a there is a limit where you take x and y are equal. So then it becomes a simple xz model on the particle lattice. And this xz model of the particle lattice has been well understood, by many various peoples. And this, xz model on the particle lattice, we know there is a phase, when the jz is much larger than the transverse component, the system forms a U1 quantum spin liquid. And this is a well-established result. So it's a so-called particle I is U1 quantum spin liquid. And this is the energy spectrum of this magnetic excitation. So you have fractionized spinons, there is magnetic monopoles, and this is emerging the U1 gauge photons. And this is a picture of so-called spinel deconfinement in this 2 hour spin ice manifold. So if you take in the Ising limit when the jz component is very, the interaction between jz is very, SD is very large, the system forms some kind of 2 hour spin ice manifold. And then you turn on this transverse component, you basically allow the system to fluctuate within the classically degenerate spin ice manifold. If you create some defect tetrahedrals, you actually create them in pairs. You can separate them by arbitrary distance because of this strong fluctuation, and it doesn't cost much energy to separate these two defect tetrahedrals. And these are corresponding to spinon deconfinement. And the line separating these, connecting these two defect tetrahedrals basically has no tension in this U1 spin liquid phase. So that's why you can separate them for arbitrary distance without costing much energy. So this is the ground state. This is U1 quantum spin liquid ground state for this XZ model. So we are going to use this result because our model can be reduced to XZ model where we take Jx into Jx equal to Jy. This is basically XZ limit will correspond to this. This is a three-dimensional phase diagram. So if you take so this is Jz, this is Jx and Jy. So if you take Jx equal to Jy, that will correspond to this diagonal direction. So in the neighborhood of this region, we know that system support a U1 quantum spin liquid. So that's using the result that the U1 quantum spin liquid is robust against any local perturbation. Even away from this x-axis limit, the system will be robust against the perturbation away from this x-axis limit. So there will be a U1 quantum spin liquid on this top surface of this three-dimensional phase diagram. But this model has a remarkable property, which is it has this permutation symmetry, permutation property under the permutation of x and y and z. So here on the top of the surface, we treat the system as a proximate model to the x-axis model. We treat the sz component as a quantization axis. Sz would be so-called emergent electric field, and Sx, Sy would be creating spin-on variables. But because of this permutation property, we can equally regard so-called Sy as a quantization axis by doing a simple permutation. Treat this Sy as your quantization axis. Likewise, you can treat the Sx as your quantization axis. So if you know the phase diagram on the top surface, you can establish a phase diagram on this corner surface and the other surfaces. But then, so this simple mathematical trick of doing this permutation of x and y, z component doesn't bring any new ingredient to the physical property of the system. So the question is whether these three U1 quantum spin liquids that are obtained by simply permuting x and y, z component, are they the same kind of U1 quantum spin liquid? So the answer is they are not. They are distinct symmetry enriched U1 quantum spin liquids. The reason comes because, as I said, this Sy component is a octupolar degree of freedom. It has different property on the crystal field, the lattice symmetry transformations. So it's a distinct type of symmetry enriched U1 quantum spin liquids. It's very different from the U1 quantum spin liquids on this surface and this surface. So then, how do we tell they are really distinct type of U1 quantum spin liquids? Now we suggest theoretically, and these three U1 quantum spin liquids are very different, because of they are distinct symmetry enriched U1 spin liquids. How do we experimentally tell the difference between them? So there is a theoretical idea. One idea is if you apply a magnetic field to the system. So because x and y components, these are so-called magnetic multiple degrees of freedom. So it does not linearly couple to the external magnetic field. Only the dipolar component, which is SD component, coupled to the magnetic field, which is this one. So all the SD component will couple to the magnetic field. So the magnetic field naturally select the SD component. Similarly, the neutron would also do that. Neutron scattering will also couple to SD correlation function. Will also observe SD correlation function. One can try to figure out what does neutron scattering actually measure. So the observation we have is that imagine in this corner where the JZ component is dominant, and the SZ would be the quantization axis for your problem. So SZ would be regarded as a so-called emergent electric field. So now we couple the system with magnetic field, which only coupled to SZ component. This is just SY component would be the electric field. So then we regard SY as the dominant component of the emergent electric field, and SZ does not commute with the SY. So what SZ does is to create so-called spin-on anti-spin-on pairs inside your U1 quantum spin liquid. When your field strength is large enough, the spin-on, the creation of spin-on anti-spin-on pair, the energy cost become very, very small. Eventually, it doesn't cost much energy to create these spin-on anti-spin-on pairs. Eventually, the spin-on will just condense. So the external magnetic field will have the property, will have the ability to drive a condensation of spin-on anti-spin-on pairs. Eventually, after the spin-on, anti-spin-on are condensed, you will Higgs out your emergent U1 gauge field. You will destroy your U1 quantum spin liquid. You will obtain a magnetic order. So for applying field along different directions, you will see the stability of this U1 quantum spin liquid and the resulting proximate magnetic orders by applying magnetic field along different directions. Yeah. So one can also, detect the evolution of this two spin-on continuums by applying magnetic field. Then, as I said, the external magnetic field, reduce the energy of creating spin-on anti-spin-on pairs. Inside this ion quantum spin liquid, it costs the final energy to create the two spin-on continuum. So there will be an exciting edge. This is a neutron scattering measurement, which only measures SZ correlation, and SZ correlation is the detection of a spin-on continuum in this context. So this the above this line, this exciting edge, these are all continuums. And if you apply field, as I said, it will reduce the energy for creating two spin-on pairs. So the energy, this is field along one direction. For different strands of field, the edge of the two spin-on continuum will evolve. It will go from this exciting edge to this one, and these are different field directions. Yeah. So this we are motivated from this cerium tin oxide. Later on, we notice there is a material which is either structure with the cerium tin oxide. This is cerium zirconate, and we convinced the experimentalist, my experimental friend, Peng Chen Dai, to carry out the experiment and see some result. I don't want to have. So Bruce Golding will talk about the experimental side of this work. So let me summarize the second part. So we have used some fundamental properties to predict some novel experiment, which due to the spin fractionalization and the multipolar structure of the local moment, there can be an emergent Anderson-Higgs transition induced by external magnetic field. So the model, actually I didn't emphasize this. So the model we derive, that can be understood theoretically, actually can be mostly solved by quantum Monte Carlo. So this is a realistic model, has application to a realistic physical system, but has no formula sign problem for quantum Monte Carlo. At the same time, it also has non-trivial quantum ground state. So this is extremely rare to have a physical model can be solved with quantum Monte Carlo, and at the same time have a non-trivial ground state. So thanks very much for your attention.
I wanted just to comment on the first part of the talk. Very similar situation was observed in ytterbium-based magnets, like ytterbium to platinum to lead and ytterbium aluminum 3. The ytterbium ion there has plus minus 7.5 a doublet in the ground state, but the effective interaction is such that it is an XXZ spin 1/2 Heisenberg model. The effective spin 1/2 is this Kramer's doublet.
Sure. Yeah. Ytterbium has an odd number electron per side. It's Kramer's doublet. Yeah. So this terrarium 3+ has 12 electrons. So it's not Kramer's ion. It's more like a non-Kramer ion, but the doublet is lowest ground state is not a non-Kramer doublet.
Yes, I understand. But the magnetic field likewise cannot switch from 7.5 to -7.
Sure.
In that sense, it also has a hidden.
Yeah, I agree with that. Yeah, sure.
Yeah, so very nice talk, and I also have a question on the first part. So the thulium system that you were talking about, that's in the same family as the ytterbium magnesium.
Yeah, exactly.
Yeah, so there's a lot of disorder in that system, right?
I'm not entirely sure about that. So
so
there was an argument by Martin Morgel saying this system, the terrain is probably too icing. So then how disorder impact on this icing degree of freedom. I think like degree of freedom is not maybe not as severe as to this Kramer's doublet, which appears for this ytterbium compound. Yeah.
So, but the disorder doesn't play any role in generating the intrinsic transverse field, right? Is that, or does it? Picture.
That's a very good question, actually. Yeah. So, no, if you want to include the effect of disorder, first of all, we have this transverse field that models the splitting between these two singlets. That's intrinsically appear even without the disorder. So if you introduce disorder, there could, create some distribution of this splitting, this external intrinsic transverse field will have some distribution. Although that expansion value will be non-zero already because of the intrinsic presence of this splitting between the two singlets.
And that could be, that splitting or the distribution in splittings could be seen with neutron spectroscopy, right? It's a crystal field.
Yeah, it can be seen, but seems right now the spectrum is very well defined spin wave-like dispersion. It's very clear.
Maybe I missed something important. I also have a question as to the first part. Your conclusion was that there is hidden multiple order, but what are really arguments of that there is a multiple order? What kind of multiple? Octopole, quadrupole, or whatever. Is the argument simply that, okay, there is something hidden in plane, but there is definitely no ordinary dipole order because it could have been, it's not seen by neutron, so it should be multiple. But are there any other arguments that it's multiple order? And what kind of multiple again?
Yeah, so
octopole, quadrupole, or whatever. Yeah. Hexadecapole. There are many different possibilities. Can you say something about that, more specific?
Yeah, that's a very good question. Yeah, so my English vocabulary is not sufficient enough to tell you this name. So you can, this is the wave function, the ground state singlet, or this is the ground state singlet, second excited singlet. So the wave function is combined of this, 6 minus 6. There's also a small part of plus or minus 3, and a very small part of 0. So this multipolar component will be this Sy, which is defined in this fashion. Will be this fashion. So the largely it will be the 12th order component. I don't know what's the name for that.
Magnetic octopole, practically, yeah. Sy is magnetic octopole, correct?
No, some people who have good English can tell whether. So this is the 12th order of multipolar order.
Okay. Wow.
So yeah, so the dominant contribution will be this 12th component of this multipolar order. Yeah.
Okay. And maybe second question actually is such type of non-Kramer doublet system like thulium. There are two options. Either you can stabilize magnetic state like complex mixture, or you really have something like structural transition, like Yanteller or whatever. We stabilize real state. So what about the structure of this material? Is there nothing special in the structure?
This is a triangle, that is.
No, triangulated, but maybe something like structural transition or maybe a modification of structure at this temperature.
No,
probably too low temperature.
No,
yeah.
I don't think so. So there are two possibilities. As I say, you are right. There are two possibilities. One possibility is the ground state is just simply a doublet.
Yeah, for example, thulium vanadate is very well-known material with non-Kramer doublet, but it evolves along Yanteller scenario, stabilizing real state and not complex.
Yeah.
But in some other material, you can stabilize complex combination.
Yeah.
So here it's more magnetic-like, yeah? That's
yeah.
Okay.
Could you show again the slide with the magnetic structure of the pseudospin in the first part of the talk?
Yeah. Sure.
Okay, so the way I read this is like a Néel antiferromagnetic order on a honeycomb lattice with the blue sides in the center having 0 moment vertically, and the other sides having plus minus along the hexagon.
That's a good point. Yeah.
So is there experimental evidence for this structure? The Bragg peak intensities agree with this?
No, the Bragg peak just tell you they only see the SD component. they don't see
Sure,
the transpose
but
common.
this plus-minus alternation with zero
Yeah,
moment.
yeah. You see that at the K point there is three that correspond to the three sublattice order. Yeah.
Yes, that's just the propagation vector.
Yeah.
But there are many structures with the same propagation vector.
Sure.
Is there experimental confirmation for this particular structure?
Yeah. So experimentally one can only see use this excitation spectrum and this the diffraction see this at a Brock peak at this K point. This is what the experimental result tells us. And as a theorist, we build up model try to whether we can expand this with very limited experimental input. This is what we do. And the reason, let me just finish it because I didn't have time to explain this. The reason it has this, the interesting quantum effect-driven magnetic order is really due to the combination of this transverse field and the very frustrated, highly degenerate nature of this Ising model, on a triangle lattice. Without this thing, it's just highly degenerate. We know that. With that, it's a quantum order by disorder effect. In a weak field regime, this central spin, this is just pointing to the transverse field direction, and this will be up, down, up, down, up, down, up, down. And this will be regarded as a linear superposition of up and down. And this is a quantum effect, and this is three sublattice order. Because the field is not that small, and in the end, the system will be strongly tilted into the y direction. The pseudo spin will be strongly tilted in the y direction, but the three sublattice structure persists. This is the theoretical explanation why the system forms a three sublattice structure of this kind. Yeah.
So if you were to apply a field along the z-axis,
yeah,
would you expect a transition from this?
Yeah, you will see some transition. Eventually, the field is large.
So, but your magnetization curve didn't show any.
Yeah, then one can think what's the reason for that. Yeah. We can talk about this later. So my student are actually doing some numeric simulation, apply field in the z direction. This model has no sign problem, so it's perfect for doing quantum Monte Carlo.
But in this magnetic structure, there should be √3 by √3 superstructure in plane. Is it seen experimentally?
Say it again.
In this magnetic structure,
yeah,
there should be superstructure √3 by √3 in plane, three sublattice. It could be seen experimentally in Newton. Is it seen?
Yeah, but they only see.
Superstructure.
No. So we can talk about this. This is much detailed. So right now, I only show the data for this Brock peak at the K point. Yeah.
Are the coupling constants known for any of the dipolar or octopolar materials? And is there any hierarchy? Is one of them much stronger than the other, the JX, JY, and JZ?
No, you are talking about there are some specific materials and ask me the parameter of this, what would be the specific parameter for this specific material. Yeah, so that's a very separate issue. If one interested in experimental data, you try to fit. This is a geometrical model. There are, other theories we try to be, universal. We try to apply our theory to be many other compound, a family of the compound. Try to figure out the global phase diagram of this system of the model that can be applied to many physical systems. So if one is interested, one can try to compare, extract some parameter for some specific material.
But is it known for any material? Are the coupling constants known for at least any one of the materials?
So I can tell you, because of this special property of the local moment, all the z component of spin is visible in the magnetic field. So if you do QY temperature fitting, the QY temperature would be minus 1/2 of Jz. So you can extract the effect of Jz. For the other two parameters, one needs to do more detailed thermodynamics as well as the spectrum measurement, and to extract the other two parameters. So here we tell the people, if the system in this kind of symmetry enriched U1 spin liquid or the other kind of U1 spin liquid, what should we expect experimentally? What can we provide a control scheme, to control the emergent excitation in the system? What do we expect the experimentally should see? So we provide this qualitative understanding, for future experiment.
Yeah, so the,
make it short.
yeah, so the final experiment, is it a dipolar spin liquid or octopolar spin liquid? The second last slide you showed.
The second and last slide.
Yeah. Next one.
The next one.
Yeah.
Yeah, so this work with my former grad student, Yao Dong Li, who is here. So the suggestion is, apart from, let's not talk about the affective disorders. The suggestion is that this material is probably, I'm not entirely sure, is because it's not in a spinized manifold at all. It's a non-spinized type of U1 spin liquid, likely. And this material is probably in a U1B phase. This is Xiaogang-Wen's notation. So B means it has a pi flux rather than zero flux. The transcendental symmetry has been realized projectively. The spin-on realized the projective symmetry projectively. So on top of that, there can be a point group symmetry enrichment. So it's called a octupolar U1 spin liquid, octupolar U1B spin liquid. This is one suggestion. This is not a firm statement. Based on very limited result of thermodynamics, we suggest it's likely to be a U1B phase with pi flux. Yeah.
Okay, let's thank the speaker again.